Hello students, welcome to EPG Pathshala. I am Dr. Mini Singh from Department of Biotechnology at Punjabi University, Patiala. This module pertains to nanotechnology and food packages under the paper of Nanobiotechnology. One of the final applications of nanotechnology in the food sector are the use of nanomaterials in food packages. What does this mean? This means that we are enhancing the value of food packages by introducing certain nanoparticles in them. What is the reason? Why do we need to do this? The conventional food packages have certain limitations, such as they don't have too much of a mechanical strength sometimes, or they do not prevent gases, the transfer of gases across the passage. So can we use nanotechnological particles or nanoparticles as part of the material of these packages, which will lend certain improved properties of mechanical as well as gas barriers? Other than this, we will also see how these nanoparticles are used within the packages and they become active packages. When we say active packages, it means that the nanomaterial enabled package has become an active package. When we say active, we will take two examples. One is an antimicrobial package. So that means we have a package which is antimicrobial. It does not let the food inside it get spoiled. How does that happen? We will understand during the course of this module. This will be followed by an example of an antioxidant film. Antioxidant film in which an antioxidant has been layered inside the conventional package, and that antioxidant further lends a shelf life to the food. The part of this module will talk about smart packages. Smart packages, they're also called intelligent packages, which means that they're intelligent enough to communicate to the consumer whether to buy the package or not. They're intelligent because they have certain dyes in it, certain indicators in it, which change color based on the change in the physical state of the food. And with that change in color, the consumer can decide whether the food inside the package is fit for use or not. Based on this module has been designed with certain specific objectives. Number one, the applications of nanotechnology in developing various kinds of food packages. And when we say kinds of food packages, we will understand in part. Number one, the improved packages. Number two, active packages. And number three, intelligent packages. When we make improved packages, one of the objectives is also how to reduce the environmental stress. We will see subsequently in certain videos, as introductory in the videos, how the discarding of these packages is causing a huge environmental stress. So can we also make packages which can be consumed? This sounds interesting. We have a package, we have put it on over a food, but then when we open that package, we can also eat that whole package. So what are we aiming at? We are aiming at reduced environmental stress. Is it possible or not? We will see in the two subsequent videos which talk about improved packages, and the second which talks about active packages and how active packaging enhances the shelf lives of food. Since this is the concluding module, let us once again look at all the applications which are pertaining to food technology in per se nanotechnology. We have studied nanoencapsulation of nutraceuticals. We have studied about nanoemulsions too. However, it is also used in sanitation of equipment, wherein we use silver nanoparticles, gelation, and as viscosifying agents too. Yet another aspect of nanotechnology in foods is the ability of these nanoformulations to do UV protection or to act as antimicrobials, to condition and abuse monitors, to develop high barrier plastics, which we will cover in the course of this module, security in anti-counterfeiting contaminant sensors. We have spoken about the electrochemical and the optical based biosensors for detection of pathogens, contaminants, and fraudulent chemicals. One other application of food nanotechnology is in nutraceuticals and nutrient delivery, which we have studied, which is in the form of nanoformulations, which can be nanoemulsions, liposomes, or solid lipid nanoparticles. These lead to vitamin fortification. Drinking water purification is another application where nanotechnology is involved by the use of nanoparticles. And sensory characteristics of supplements can also be enhanced by the use of nanoparticles. Yet another application is in targeted genetic engineering, identity preservation, agrochemical delivery, and sensors to monitor soil conditions. We have spoken about sensors for foods. There are various approaches of nanotechnology to develop processes and products. These are broadly classified into two types, the bottom-up approach and the top-down approach. In the bottom-up approach is a kind that we will study in the food packages, is where we use nanoparticles, impregnate them into certain materials and enhance the properties of those materials. In top-down approaches, as we studied in the preparation of nanoformulations, we reduce the size of a macromolecule, bring it to a nano dimension and enhance its properties. Talking in specific about food packaging, the global nano-enabled food and beverage packaging market was envisaged to grow since 2008. Scientists and industry stakeholders have identified the potential uses of nanotechnology in food packaging, pathogen, gas or abuse sensors, anti-counterfeiting devices, UV protection, and stronger, more impermeable polymer films are the realm of nanotechnology in food packaging. The reason why food packaging applications are gaining impetus in the food sector is because of their out-of-food applications. In this case, the nano-enabled materials are only in contact, not in direct contact with the food material, but they're only lending their properties to enhance the properties of the food package. Therefore, there is no direct contact or presence of these particles within the food matrix. The reason why nanomaterial enabled food packaging has been developed is to overcome the limitations of conventional food packaging. The two main barriers or limitations in conventional food packages are its weak mechanical properties and weak barrier properties. When we say weak barrier properties, we are essentially meaning the barrier properties to moisture as well as certain gases. And one third factor is their non-biodegradability. Not essentially that nanoparticles will be able to counterfeit the non-biodegradable nature, but they will definitely be able to enhance the mechanical as well as the barrier properties of these new age materials. Therefore, nanotechnology-enabled food packages have been developed, and they are broadly classified into three categories. Class 1 are improved packages, Class 2 are active packages, and Class 3 are intelligent or smart packages. Improved packages mean wherein the conventional packages, the structure or the mechanical properties of the conventional packages have been improved by impregnating them with nanomaterials such as nanoclays. In active packaging falls the antimicrobial packaging as well as the antioxidant films. It is these active packagings which enhance the shelf life of foods. In intelligent or smart packaging, there are certain sensors which interact with the consumer, and by looking at the package, we can tell whether the food is fit for consumption or not. Therefore, these are classified as intelligent or smart packages. By understanding the three main classes of food packages, let us understand now the potential benefits of using these nanotechnology-enabled packages. Their arena is broad. It spans antimicrobial properties, UV protection properties, oxygen scavenging, meat or fish spoilage prevention, pathogen detection, freshness indicators, gas barrier properties, and time temperature indicators. When we talk about oxygen scavenging, it is important to note here we are not merely talking about a barrier to oxygen transfer, but also making films which scavenge reactive oxygen species. By using these nanoparticle-enabled carriers formulations within the food packages, we are able to enhance the shelf life of foods, thereby adding value into the food sector.
At the grocery store, Most foods come wrapped in plastic packaging. Not only does this create a lot of waste, but thin plastic films are not great at preventing spoilage. To address these issues, scientists are now developing a biodegradable film made of milk proteins. And you can eat it, to boot. Led by Peggy Tomasula, the team at the U.S. Department of Agriculture developed an environmentally friendly film made of the milk protein casein. These films are up to 500 times better than plastics at keeping oxygen away from food. And, because they're derived from milk, they're biodegradable, sustainable, and edible. The researchers are presenting their work at the 252nd National Meeting of the American Chemical Society. Although the researchers' first attempt using pure casein resulted in a strong, effective oxygen blocker, it was relatively hard to handle and would dissolve in water too quickly. So they made a few improvements, adding citrus pectin into the blend to make the packaging even stronger and more resistant to humidity and high temperatures. The material has a number of unique applications. In addition to being used as plastic pouches and wraps, this casein coating could be sprayed onto food, such as cereal bars or flakes. Right now, cereals keep their crunch in milk due to a sugar coating. Instead of all that sugar, manufacturers could spray on casein protein coatings to prevent soggy cereal. Co-leader of the study, Laetitia Bonai, says the team is currently testing applications such as single-serve edible food wrappers. Individual dried soup portions, or instant coffee wrapped in the film, can be added to hot water where the film readily dissolves, eliminating the packaging waste. Because single-serve pouches would need to stay sanitary on store shelves, they would have to be encased in a larger plastic or cardboard container to prevent them from getting wet or dirty. Tomasula and her team hope that, in the future, their casein-based film can help foods keep fresh during shipping while decreasing the amount of plastic waste entering landfills. Headline Science is produced by the American Chemical Society. For more on the latest chemistry headlines, subscribe to the ACS YouTube channel.
We're all wasting more food than ever. Up to half of the world's produce, according to Britain's Institution of Mechanical Engineers. Their report, released last week, says that with a rapidly growing global population, policymakers need to find smart solutions to prevent waste and make food go further. These scientists at Spain's Tecnalia Institute believe they can help. They're developing 3 methods of active packaging designed to preserve food for longer. Techniques that researcher Ilana Diaz de Apodaca says will stop the rot. Literally.
One of them is the incorporation of an active component directly in the packaging material, like we are doing here. Another option is the application of a layer and coating to the packaging. The third option is to place an active layer directly on the surface of the product.
The team used natural antifungal compounds like pectin and chitosan in their research. Laura Fernandez says natural additives added directly into this packaging's ingredients will help the cheese stay fresh, even after it's been opened.
By doing this, we can increase the lifespan once the packaging is open. The growth of mould is a big problem, so incorporating an antifungal component permanently in contact with the cheese will allow us to extend the cheese's lifespan once it's opened.
The team says all 3 methods being tested allow controlled migration of beneficial additives, as well as offering health and environmental benefits.
The use of synthetic preservatives is being questioned because of health concerns, for example, such as allergies. And consumers are demanding natural preservatives together with environmentally friendly packaging materials.
And with some of these environmentally friendly materials edible, there'll be even less waste to throw away. The greatest challenge, they say, may be in persuading consumers that edible packaging is an acceptable alternative. But either way, the Tecnalia team believe their work is food for thought.
Let us now begin to understand in detail each class of these packages, the first being improved packages. Improved packages are those wherein polymer nanocomposites have been embedded within the conventional sort of polymers. The most commonly used nanocomposites which are used within these materials are nanoclays or silicates. In this kind of packaging system, the nanoparticles present in the packing materials improve the packaging properties by acting as gas barriers and also provide temperature and moisture stabilities. In addition to this, it also provides a heightened tensile strength to most of these packages. Let us now see how, when we use these materials or clays within the polymers, what happens and how does gas barrier property or moisture property enhance. Looking at this image shown, there is a difference in the structure of microcomposites and nanocomposites. Figure A shows the clay platelets within the polymers. If there is gas barrier, there will be limited gas barrier in the microcomposite vis-a-vis the use of nanocomposites, wherein their impregnation into the polymer matrix renders a heightened surface area, which will improve the barrier properties of the composite film. The image shown depicts the preparation of nanocomposites and their improved barrier properties as compared to native polymers. Native polymers, which are used conventionally in the development of food packages, in those carriers, there is straight diffusion path, there is a direct perpendicular passage of oxygen through the package, which leads to weaker barrier properties. Whereas, if we use different kinds of nanoparticles, whether nanoparticles, nanoplatelets, tubes, fibers, or nanowires, which are dispersed in one of the nanostructures in the polymer, and as shown in the structure, it leads to a tortuous diffusion path, which means that the path is no more simple for the oxygen to diffuse within the barrier. It has to undergo a much longer path length. Talking about dispersing these nanoparticles within the carrier molecule, they can be placed in different forms: tactoids, exfoliated, and intercalated. Depending upon their forms, the barrier properties can be changed. The figure shown here exemplifies once again the direct passage of oxygen in A vis-a-vis a tortuous barrier of oxygen in a polymer impregnated film, which is B. These polymers could be silica nanoparticles, carbon nanotubes, nanocrystals of starch, cellulose, nanoviscors, chitin or chitosan nanoparticles, and some other inorganics. They are also stronger, more flame resistant, and possess better thermal properties and increase the shelf life of foods in comparison to native polymers with no nanofillers. Shifting attention now from improved packages to active packages, here we will be talking about metal nanoparticle embeds as antimicrobial agents. These kind of packages are one form of example of active packages. In these, silver has been used as an antimicrobial agent. It has been known that silver has been used as an antimicrobial from ancient times. It is shelf stable for long periods of time and is safe for humans and other higher order organisms. Both silver and titanium dioxide nanoparticles with enhanced antimicrobial effect can be incorporated into food packages to improve the shelf life of foods to a greater extent. A step ahead are the intelligent packaging materials. The sell-by date for a carton of milk may indicate to a consumer that the product should be good for a period of 2 weeks, but this date may no longer be applicable if that milk was stored above its optimal temperature for an hour. So to say that if we are about to buy a packet of milk from the market and it was lying at an ambient temperature, it would have already got spoiled or in the process of spoilage, whereas a package of milk which is kept under frozen temperatures would have heightened shelf life. Through bottom-up engineering, nanomaterials can be manufactured which detects the presence of gases, aromas, chemical contaminants, and pathogens, or respond to changes in environmental conditions. This is not only useful for quality control to ensure that consumers are able to purchase products at their peak of freshness and flavor, but also improves food safety and reduces the frequency of food-borne illnesses. The figure here shows the key components of a typical active packaging film. On the lower right is a food which is packaged in a food packaging material having a headspace. On the horizontal gray line that is seen shows an indicator, which is an indicator that communicates with the consumer. What this indicator holds is nano-encapsulated or nanocomposite containing material, which will indicate the freshness of a product to the consumer. This will be understood more clearly in examples that will follow. One of the key features of food packages is to prevent the transfer of gases. Gases, as we have already understood in the course of the module, are results of bioactivity or respiratory activity of food as the food is stored for a longer time. So when we are able to detect these gases, we cannot see gases. So we have to devise a way to detect gases. When these gases accumulate inside a food package, it starts deteriorating the food. So what we will see in the subsequent videos is how certain packages have been developed which begin to indicate to the consumer the freshness or non-freshness of that package. This is an example of an indicator of oxygen. Most of the foods, perishable foods, will emit certain gases, particularly oxygen in case of meats. So that oxygen barrier, which means that we need to keep oxygen away from this barrier, for which we need a barrier, a food packaging material with good oxygen barrier properties. Now, whether a food package material has an effective enough barrier property or not can be tested by these indicators. In figure A, you can see two dots. These are the packages, or these are the dots of titanium dioxide in combination with the methylene blue reduction indicator dye. These titanium dioxide nanoparticles are activated in the presence of UV light. So in figure A, the package is freshly sealed and both indicators are blue. In figure B, the indicators are activated by the use of UVA light. After a few minutes, the indicator outside of the package returns to blue color as is seen in C, whereas the indicator in an oxygen-free environment remains white, which means that in C, the food is still fresh, which is because it does not come in contact with oxygen. The moment we see the oxygen permeating into this packaging film, that means there is not good enough barrier property. There is contact of oxygen with the meat, which will lead to food spoilage. And the indicator turns blue, which will tell us that this kind of package is not a favorable package to purchase. This is a similar example which was depicted previously. Again, but in this case, the sensing element is temperature. The bottle on the left shows an indicator which is blue, on the right which shows an indicator which is white. It merely shows that the bottle on the left was stored at refrigerated temperatures, whereas the one on the right was stored at ambient temperatures. In summary, nanotechnology has immense potential and offers a better food packaging systems. These innovative packages are aimed at environmental sustainability and reduced food losses. Nanotechnology packages include biodegradable edible polysaccharides and proteins as part of their package, where we talk about edible packages, active packages to enhance shelf life, and intelligent packages which involve bio-induced indicators. There is a need for more research on the behavior of nanoparticles in the food and their safety profile before we can begin to think about commercialization of any of these nano packages. Nonetheless, these kind of packages have huge potential in the near future. Thank you.